Hi, I'm Deepti, and today I'm going to be talking about the physics behind trampolines.
So let's get started. The first trampolines ever don't have a specific date as to when they were used, but were used by Eskimos and were made out of walrus skin to throw each other up into the air. Later, trampolines were made in 1934, used solely for the purpose of either astronaut or sports training. Over time, the popularity of trampolines grew as a recreational activity, and they now even have their own event in the Olympics. Personally, I got a trampoline a couple years ago, and I think it's a really fun pastime and workout at the same time, so it's kind of a two-for-one deal. Alright, now it's time to move to the physics portion of trampolines. Energy and Newton's laws of motion are the primary physics aspects behind jumping on a trampoline. Kinetic and potential energy are the factors that allow you to jump higher on a trampoline than you ever could on flat ground. With potential energy also comes gravitational potential energy and the potential energy stored in springs. Let's start off explaining the kinetic energy behind trampolines. The formula for kinetic energy is Ke equals a half mv squared, where m is mass and v is velocity. When you constantly jump on a trampoline, your body has a changing amount of kinetic energy over time. Your velocity doesn't remain constant during your entire duration of jumping, so your kinetic energy increases and decreases in increments as a result. Your kinetic energy is at its highest right before you hit the trampoline as you head back down, and the moment you jump off the trampoline and head up. Your kinetic energy is also at zero at the highest peak of your jump when you're about to descend, and right before you're heading up but still touching the trampoline surface. Next, we're going to talk about potential energy's role in trampoline jumping and connect that back to kinetic energy. The formula for potential energy is Pe equals m times g times h, where m is mass, g is the gravity constant, and h is the height. A typical rule states that the higher you are, the more potential energy you would have. In addition, people who weigh more than others have a greater potential energy because of gravity, so they have more trouble jumping to higher heights since gravity pulls them down. Going off of what I said before about kinetic energy, as you're traveling upwards, your kinetic energy decreases the higher you are, eventually reaching zero at the peak of your travel. This basically means that your velocity is decreasing and you're slowing down. The simultaneous slowing down but increasing height results in your kinetic energy being transferred into potential energy. So once you head back down, your decreasing height results in decreasing potential energy because that potential energy is being converted back into kinetic energy. The reason for this transformation of one type of energy into the other is due to keep the total amount of energy in the system constant, as stated by the law of conservation of energy. In addition to kinetic and potential energy, we need to talk a bit about Hooke's law. The formula for Hooke's law is F equals negative kx, where k is the spring constant and x is the displacement of the spring. Hooke's law acknowledges the springs involved in trampolines and also ties it back to the concept of equilibrium. A trampoline can be broken into two basic components: an elastic disc, which acts as the base, which is upheld by the second component, numerous springs. When you jump in at the surface of the trampoline, the surface stretches out and the springs expand due to the force your body exerts onto it. What Hooke's law tells us is that when someone bounces and comes back down to hit the trampoline, the springs attempt to work in order to return back into equilibrium and pull back against the weight of your body. This is another representation of potential energy, but it is related to spring constant and Hooke's law. Now last but definitely not least are Newton's laws of motion, the fundamental principles of physics. All three of these laws are in some way incorporated into explaining the physics behind trampolines. Newton's first law states that every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. Without this law enforced, you would either fly into the sky when you jump up or fall straight through the bottom of the trampoline on your way down. You have gravity and the mini springs to thank for keeping you bouncing. Newton's second law summed up states that force equals mass times acceleration. Without this equation, equations for kinetic energy can't be obtained since acceleration is just gravity. Then lastly is Newton's third law, which states that for every action there is an equal and opposite reaction. Hooke's law goes hand in hand with this, as when springs get stretched out, they have to retaliate by eventually compressing to reach equilibrium and send you flying through the air.
This is Newton's first law of motion. These springs show Newton's third law and Hooke's law paired together, so when someone jumps on the base of the trampoline, these springs extend and then they work back to contract against the force exerted onto the trampoline by the person. So that's all you have to know about the physics of trampolines.